closed loop. Okay. So transmitter uh, is a sensor. You can call a sensor a transmitter. Is that correct or not? A sensor is a transmitter. A sensor is not a transmitter. The work of sensor is to sense a physical change. Okay, it will change its entity. Transmitter can be a sensor. Yes, Bhanu, you can say that a transmitter can be a sensor. There can be an arrangement where your voltage output is directly fed to the current loop, or if there is a voltage loop, to a voltage loop. But for in a general statement, a sensor, all sensors cannot be transmitter. Okay, okay, all sensors cannot be transmitter. Okay, we already discussed that. Okay, so I think Sachin had said yes, Sunidhi said yes, Raj Nandini said yes, Khushbu Kumari, Aprajita, Ritik, Hitesh, Bhanu. Let me clear your doubt. We discussed it earlier also. Yesterday only we have discussed that a sensor indicates a physical change to a system. Okay, we had taken an example of RTD. Okay, what RTD does is it is a what is the full form of RTD class? It is resistance temperature detector. So it changes its resistance because of temperature. It has a voltage supply. Okay, so the voltage supply and you can say generally it is a platinum you can say shaft or rod that detects the temperature, which changes its resistance. Okay, so when it changes its resistance, the applied voltage gets different. Okay, and that voltage is processed, okay, and sent to the current loop. That voltage is processed and then sent to the current loop. Okay, that processing and collection of that particular voltage is being done by your transmitter. Okay, so sensor and transmitter are two different things. In a very general language, mostly most of the PID engineers, they say sensors as transmitters or transmitters as sensors. Okay, in a general language, it is very prominent that you will listen. But technically, sensor and transmitter are different. Okay, so the sensor is just detecting a particular change in a physical phenomena. It is just sensing it, whether by changing of resistance, whether the changing of position, whether the changing of you can say current, or you can say voltage. But what transmitter is doing, it is transforming that change, that particular change, into a suitable voltage or a processed voltage that has been fed to your current loop for analog sensors. Okay, so I need this answer from Sunidhi, Sachin, Rajnandini, Khushbu, Ritik, Aparajita, Hitesh, and Bhanu. Are you aligned now? Am I saying correct? Or do you have any doubt? Okay. We had a session yesterday for this, and Mr. Ryan told it very clearly, but we need to repeat it. Okay. That is why I'm asking these repetitive questions, because I know that sometimes things skip from our mind, but when we repeat few important things, it is always going to work. Okay, so by that note, let me just ask one another question to you. Uh, what is what was the issue? What will you do when your range is very short? For example, for the entire process, for the entire process, you can get 4 to 20 milliampere, and we already discussed it yesterday that 4 to 20 milliampere range should be fully occupied. Okay, so it is very much you can say beneficial for use for us to use, and important also for us to use 4 to 20 milliampere range. But for any reason our range has been constrained to say 7 to 12 milliamp, then what we are going to do? What are the things that we can do? Change in load resistance or recalibration, change transmitter amplification. Yes, yes, Ritik, very correct. Bhanu, very correct. We discussed it in the previous session also. Okay, yeah, use better receiver having higher accuracy. Yeah, but can receiver change the range? How a receiver can change the range? No. We can. Huh, that can be done. Yes, that can be done. But again, yes, we can always use a better receiver which have high accuracy. But Nayan, with this, there arises another question, which will be an optimum solution to change receiver and get better accuracy, or changing in the loop? And what will be the tough task and what will be an easy task? Yeah. So if you are ready to change your loop characteristics, for example, load resistance, recalibration, or change in your transmitter, about the function of transmitter, then this is a very good. This is a better option as compared to use better receiver. Okay, class. Uh, Now I have one more question. So now you know that we can't use a zero. We try to not to use a 0 milliampere output, or our range doesn't start from 0 milliamp. There are two reasons for that. Can you answer me the two reasons? What are the two reasons, class? We use 4 to 20 milliamperes. We don't use 0 to 20 milliamperes. Why? We won't be able to tell if breakdown occurs. Okay. Very good, Bhanu. Very good, Ritik. Difficult to maintain zero every time. Error is present or not. Okay, there is an issue. Error detection is difficult. Okay, okay, okay. Only three answers. Only 3 to 4 answers. Okay, one more question to you all. Answer this question. Error detection, yes, correct, Kalpana. So my next question to you is that, yeah, difficulty in error detection, that which type of loop is preferable, which type of loop is more noise immune, which type of loop is more noise immune. Correct. Okay, and what was the reason behind that? Low impedance. Okay, okay, correct, very correct. Yes, very correct. So now I think our sensor part is covered. We have taken very basic principles, working principle of sensors, and that theoretical part is in your theories also. We have covered those basic principle also. A very quick view of that basic working principles of all the sensors, how sensors work. But we have looked more into the integration of sensors into a particular factory automation system. Okay, because that is important thing. Okay, now we will shift to actuators. Okay, so my question is that what are actuators? Can you answer this question? What are actuators? How many kind of actuators have you seen, and how many kind of actuators do you know are there in industries? Maybe that helps in providing motion. Okay. Yes, partially correct. Partially correct. Actuator helps in moving or controlling a particular system. Okay. Helps in providing controlling to machine. Okay. Okay. It is responsible for moving and controlling a mechanism, provide controlled and sometimes limited movements. Yes, correct, 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 very correct. Few more answers? No. Okay. So the question is that yes, very correct that actuators actually actuate a particular movement, or what they do is they can provide a movement also, and they can also provide a certain, you can say, current, or you can say any kind of actuation for a particular process it can provide. Okay, so these are your actuators. And what is the most prominent kind of actuator that you might have seen in industry? And we have seen many industry videos also. And what was the most prominent kind of, for as far as factory automation is considered? Yeah, hydraulic and pneumatic. Yes. Yes, hydraulic and pneumatic. So this pneumatic is very much important, and even hydraulic is very much important in industries. And as an automation engineer, or as an uh, engineer, it doesn't matter what kind of profile you are. Pneumatic and hydraulic, the very basic understanding of hydraulic and pneumatic is very much necessary. Okay, we are not going to get deep into these concepts, but still an overview that how these works, because when you are going to concern about a particular system, these are not pneumatics now, these are electro-pneumatics. Okay, so if you don't know that what a directional control valve does and how it operates, you can't comment about the electro, you can say, electro-pneumatics or the solenoid that is uh, used for operating, or you can say operating that particular DCB. Okay, so that is why it is very much important that we should have a very brief introduction of what we say industrial pneumatics. Okay, so we will take 2 to 3 days in completing pneumatics and actuators. Okay, I will not go very much deep into that, just a very brief introduction. Okay, so that, and I'm not going into the software which is responsible, which is used for simulating pneumatics, because that is not something that you should know. The only thing that you should know is that how to interpret a pneumatic circuit. Okay, this is your job, that how to interpret a pneumatic circuit and how to understand that what is going into a process through pneumatics. Okay, so once we are covered with pneumatics, we are going to take few servo motors also, motors, servo motors, DCVs, and that will be our learning path. Okay, so let us just start with the PPTs now, and we will have a very good look at the video also. Let us first look at the Festo video. So the industry that is responsible for all, which is the pioneer in pneumatics, is Festo. Okay, so let us just have a very quick review on what Festo is saying. Just give me a minute. I have some internet issue. My LAN is not working. I'm working from mobile. Just give me 2 to 3 minutes. Let me sort this out and I'll come back to you. Okay? Just 2 minutes. Yeah, welcome back, class. Okay, so we will just continue with a video of pneumatic control by Festo Didactics. Don't get I want to say that please, this video is a little bit old, but you should understand that from what time pneumatics has came into industry and what is the core of existence. Okay, so how much core it has existed into the industry, that although this video is old, but it is very relevant for automation till now, because all these technologies are same, they have not changed from the due time. Okay, so these technologies are same, the video is a little bit old, but please don't mind that. Okay, so let me just share my screen now. Is my screen visible to all of you? Yeah. Okay, Tish. Yeah, thank you. Thank you. Okay, so this video is just for to show you that how pneumatics operate, and it is just a 1 to 2 hour video, which is a combination of all these concepts. And once you get through this, you will be easily understanding a particular system. Okay, it is very easy, and just it is a little bit different from your course line of electronics and communication, but it is very much relevant in industries. Okay, I'm not going deep into the concepts of what we say simulation of pneumatic simulation, but this is important because you will deal with pneumatic circuit diagrams. Okay, so interpreting those diagram is also one issue. Okay, so now let us continue with this.
What you see here isn't magic. It's simply air being used to transmit energy. Air is in plentiful supply everywhere. When air is compressed, it can be used to perform work. This is known as pneumatics. Here, air pushes on a device, moving it back and forth. It's controlled by a simple pneumatic control system. Pressing the button sends air to the cylinder. The control valve in the center of this circuit determines which side of the cylinder receives the air. The push-button valve at the bottom of the circuit sends signals to the control valve. Therefore, compressed air acts as both a working and control medium. Pneumatics, or using compressed air to transmit energy and control functions in systems, has several advantages. Let's examine examples of each. Compressed air is fast. For example, short cycle times can be achieved in automated assembly applications. At the same time, it is overload safe. If the machine jams, pneumatic motors or circuit components will not burn out. Another advantage is that compressed air is clean. This is very important in the textile and food industries, where sanitary conditions are of primary importance.
So now can you tell me the advantage of pneumatics, that why pneumatics is so much relevant for industries? Fast overloading is not an issue. It is safe and clean. Yes, correct. I need answers from others also. Again, answer can be repetitive, but I need answers. Class, I need answers. Please respond on the chat box. What happened? Abhay, Adarsh, Alok, Ankush, Aparajita, Bhanu, Hitender, Hitesh, Kalpana. Yeah, it has speed. Yeah, it is fast, it is safe, and it is clean. Yeah, yeah, yeah. Okay, okay.
Pneumatics is also safe because compressed air does not burn or explode under a wide range of operating temperatures. In addition, the exhaust air can be discharged directly into the atmosphere. Pneumatic systems are heavily utilized in cleanroom applications for the same reasons of cleanliness, low combustion, and fast operating speeds. Compressed air can also be stored, ready to be used when required. Another advantage is that compressed air does not break down when exposed to high temperatures, thereby allowing for safe, consistent operation under a wide range of temperatures. And finally, the individual pneumatic components are inexpensive when compared to other forms of energy transmission and control. Pneumatic control and actuation is an ideal energy for automation of industrial processes. few basic principles of physics enables you to gain a better understanding of pneumatic systems and how they function. Let's start by defining pressure. Atmospheric pressure is present everywhere on Earth. It's generally regarded as being a constant at sea level of 100 kilopascal, abbreviated kPa. All pressure measurements taken using atmospheric pressure as the 0 point are designated gauge pressure, or P sub G. Pressure gauges attached to pneumatic circuits usually indicate pressure as gauge pressure. From this point on, whenever P is used without a subscript, it is indicated in gauge pressure. Absolute zero pressure is 100 kilopascals below gauge pressure. Any pressure below gauge pressure is called vacuum, or P sub V. Therefore, absolute pressure is the sum of vacuum and gauge pressure. Like all gases, air has no particular shape. It assumes the shape of the container. When air is compressed, it's storing energy. When the compressed air is released from the container, it can be used to perform work such as moving an object. In summary, the mechanical energy of the piston pump moving in and out can be converted to compressed air. The energy can be stored in a container, in this case, the balloon. As needed, the energy can be converted back to mechanical energy, as demonstrated by the toy truck. Another example of the conversion of energy. In this case, the air pressure generated is applied directly to the cylinder. The force generated by the compressed air is then converted by the cylinder back to mechanical energy, lifting the load. Next, let's study the relationship between volume and pressure. The volume of this cylinder is 2 liters, and the pressure, as indicated on the gauge, is 100 kilopascal. This relationship can be described by the formula V times P equals a constant value. To test this, let's enter the two values into the formula. Multiplying these two numbers results in an answer of 200. When you press down on the piston, reducing the volume in the cylinder to half its size, the pressure gauge now reads 200 kilopascal. Applying these new values to the formula results in an answer of 200. Pressing down on the cylinder until the volume is cut in half again results in a volume of 1/2 a liter and 400 kilopascal. The new numbers again equal a constant value of 200. This example demonstrates the relationship between pressure and volume. For all of the volumes, the product of the two values remains constant. Next, let's examine an application of this concept. If you have a compressor with an output of 7 to 1, you can use this formula to determine its output pressure. The known values are the starting atmospheric pressure P1. Formula V1.
This is a very simple formulation. This is important.
The compressed air used in pneumatic circuits must be clean and dry. Let's examine the devices used to produce compressed air. Compressed air can be produced using stationary or mobile compressors. Both types use various designs to compress the air into a smaller volume. Two of the most common types are piston and screw compressors. The drawing on the left represents a reciprocating piston compressor. When the piston moves down, it draws air into the cylinder. It then moves up, compressing the air. Compressors that contain one cylinder are called single-stage compressors. Each stroke of the piston produces a burst of compressed air. The screw-type compressor consists of two threaded shafts that are intermeshed. As they turn, they transport air from the intake side to the compression side. One advantage of this type of compressor is that it produces a continuous flow of air. In both types, as the air is compressed, energy in the form of heat is concentrated in a smaller space. So most compressors include a cooling unit to reduce the temperature of the compressed air. Such units can also be used to reduce moisture, oil, and dirt in the compressed air. The compressed and cooled air is then stored in a tank called a reservoir, which performs several functions. It acts as a buffer, smoothing pressure fluctuations as the air is used by the circuit. This also allows the compressor to run only when needed to pressurize the reservoir. The reservoir also supplies a steady flow of air to control circuits. This reduces fluctuations in pressure under varying rates of use. In addition, the reservoir helps to cool the compressed air. As the air cools, moisture separates from the air and collects in the bottom of the reservoir. This water must be drained from the reservoir on a regular basis.
So class, kindly focus on this. You have seen that these reservoirs are to be cleaned, or you can say are to be needed to be drained. Why? Because this air, the moisture in air collects into the bottom of your compressor, and when this moisture is of a very high limit, then it can go into your system also. Okay, so compressed air along with moisture is going to damage your system. Okay, so this drainage is very much important, and during the maintenance scheduling also this draining is now done automatically. Okay, so we have a certain moisture sensor, or you can say level sensor, associated to your compressor, and it gets auto drained from that part. But again, safety is a very important issue in this, and a lot of technology is involved in this particular process. But this process is now being automated in industries, in various industries. Okay, and since it is automated, it is of your interest that yes, these kind of operations are required to be done. So this is a kind of your preventive maintenance. Okay, so this is a kind of your preventive maintenance, that you are maintaining a particular system in order to prevent a breakdown. Okay.
Not all of the moisture is removed in the reservoir, so in order to prevent corrosion of valves and other components, a dryer is often included in the system. When designing and installing a compressed air system, the distribution of the air has a major effect on system performance. The size and layout of the pipes is critical for economical operation of the system. The design should also allow for future increases in demand because modifications can become very expensive. Connections to the main piping should be done from above to prevent water from flowing into the machinery. The system should also include fixtures that allow water to be drained off. In addition to the preparation of compressed air during its production, a service unit is used to prepare the air when it enters the machine circuit. These cutaways show the intricate air passages typical of pneumatic components. It's important to remove dirt and moisture that may have been picked up by the compressed air from the distribution system. Dirt could clog component air passages, and water could cause corrosion of valves and fittings. This is a cutaway of a typical service unit. It has four main features. Let's identify each one. It contains a filter element, condensate bowl with drain, pressure regulator, and lubricator. In addition to removing particles carried by the air, such as rust, the filter also removes moisture. The moisture is collected in a bowl attached to the regulator that should be emptied on a regular basis, then removed and cleaned. The filter element should also be replaced when it becomes coated with dirt, such as rust particles. Air pressure in the distribution system is normally higher than that in the machine circuits. The pressure regulator on the service unit controls the pressure entering the machine. Some pneumatic systems use components that require lubrication. The lubricator in the service unit, when filled with oil, adds an oil mist to the compressed air, but oil should not be used in applications requiring sanitary conditions. pneumatic cylinders are used to raise and lower manufacturing tools. This is an example of how pneumatic actuators convert energy in the form of compressed air to mechanical energy. To understand how they function, let's study a number of types of linear actuators. This is a transparent model of a cylinder. A linear cylinder is the most frequently used pneumatic actuator. Compressed air energy is converted inside the cylinder into linear motion. Cylinders are available in a wide range of shapes and sizes, normally within the following specification ranges: bore 6 to 320 millimeters, stroke 1 millimeter to 2 meters, force 2 to 50,000 newtons, piston speed 0.02 to 1 meter per second. Now, let's examine how cylinders function. This is a single-acting cylinder. It's represented by this ISO symbol, which indicates that the cylinder has one air inlet port and a return spring. When compressed air is supplied to the inlet port of the cylinder, it pushes against the piston. If the force generated by the pressure is greater than the force of the spring, the piston moves.
So class, just focus on, it is very important for you to focus on the symbols also, because as an engineer you need to deal with the manuals, and you have to interpret the manuals also. Okay, so for that these are very simple symbols, not very much complicated symbols. Okay, so just have a look at the symbols also, because we will have a practice where we need to understand you can say a pneumatic diagram for a whole system. Okay, so a very keep a notice on the symbols also, and that is important. Okay, okay.
Away from the inlet port, compressing the spring and extending the piston rod. When the pressure is released, the spring moves the piston back to its initial position, retracting the piston rod. The force of the spring, air pressure level, and piston area affect the work capacity of the cylinder. Single-acting cylinders perform work only in one direction, the extension of the cylinder. They are used in applications such as clamping or the ejection of workpieces. In applications requiring work in both directions, the double-acting cylinder is used. This is a double-acting cylinder and its ISO symbol. Note that it has two inlet ports and does not contain a return spring. In a double-acting cylinder, the force exerted by the compressed air can be directed against either side of the piston. This allows work to be done on both the extend and return strokes. Note that the area occupied by the piston rod also reduces the force generated on the return stroke. Due to the area occupied by the piston rod, less air is needed for the return stroke. When selecting a cylinder for a specific application, you must take various factors into account: stroke length, extension force, and retraction force. And finally, cycle speed. Next, let's examine the relationship between force and speed. In this example, with equal loads, both pistons extend at the same speed. If the load on the left is increased, the cylinder extends more slowly. If yet more weight is added to the load, it slows even further. So, with equal pressure and cylinder size, increasing the load decreases the actuation speed. If a load is applied which equals 75% of the cylinder's capacity, the extension speed will equal 1/2 the speed when there is no load. Next, let's examine the effect of changes in pressure. Here, a cylinder under load is extended using an operating pressure of 380 kilopascals. If the weight of the load is doubled, the cylinder will not extend until the pressure is increased to 600 kilopascals. This demonstrates that there is a direct relationship between operating pressure and load. Next, let's study the effect of changes in cylinder bore size. The bore size is the inside diameter of the cylinder. These two cylinders have different bore sizes. Using the same pressure and load, the cylinder on the right cannot lift the load. However, the cylinder on the left with the larger bore size is able to lift the load. Let's measure the difference in force.
So in order to lift a heavier load, do we need to change the cylinder or just increasing the pressure can work? Class, can you answer me this question? If you want to increase the load, do we need to change the pneumatic cylinder or just increasing the pressure will work? Yeah. Yeah, both can work because you know that force is pressure into area. Okay. So when you are increasing the pressure, then also it can work. And when you are increasing the area, because pressure is always going to be constant because the constant pressure is supplied to it. Okay, so increasing the pressure will work and also increasing the bore size or area. Okay, so that piston area is increased. So normally for heavy load, if we can't give higher pressure, we increase the bore size. Okay, so when we increase the bore size, now one more question: if we increase the bore size, will the speed of operation increase or decrease? If we increase the bore size, Ritik says it increases. I am asking about the dimension bore size. That means the diameter of the cylinder. If I am increasing the diameter of cylinder, whether the speed will increase or decrease. Class, kindly answer this question. I need answer from everyone for this question. Bhanu says it will decrease, it will decrease, it will decrease. Yeah, yes, it will be decreasing. Why? Because area is increasing, more and more air is required. Okay, so for a larger volume to cover, it will take more time. Okay, okay, I think yeah. So some corrected also. Okay, okay, good.
The small cylinder shown here has a diameter of 16 millimeters. It exerts a force of 106 newtons when operated at 600 kilopascal. A cylinder with a diameter of 25 millimeters using the same pressure exerts a force of 262 newtons. When the same pressure is applied to a 32 millimeter cylinder, a force of 418 newtons is produced. This relationship can be shown by the formula force F equals piston area A times the pressure P. The diameter of the piston directly affects the force, speed, and air consumption of the cylinder. The most efficient design uses the smallest cylinder adequate for the application. In this machine, various size pistons are used based on the job to be done. For example, the movement of materials requires a different force than clamping or the movement of heavy tools. There are some applications where the full speed is not desirable at the end of the cylinder travel. These applications require a cylinder with adjustable end position cushioning. This feature slows piston travel at the end of its stroke. End position cushioning is accomplished by restricting the flow of exhaust air during the end of the stroke. This results in the air being compressed in the cylinder and opposing the movement of the piston. Next, let's examine other types of cylinders. For example, this double-acting cylinder has a double-ended piston rod. This design provides more precise linear movement due to the two bearing surfaces. When heavy tools are not mounted along the axis of the cylinder, their weight applies forces to the side of the cylinder that can be compensated for by double-ended piston rods. Another advantage of double-ended piston rods is that the ends not used for the application can be used for other functions, such as end position sensing. Another type of cylinder design has a hollow piston rod. This can be used to hold wires connected to a device at the end of the rod, such as an electromagnet. Or it can be used as a passage to carry vacuum or liquid such as oil. These cylinders have a fitting on the end of the rod for the connection of the tubing. This cylinder has no piston rod. Built into the piston is a ring-shaped permanent magnet. Mounted on the outside of the cylinder is a part called the yoke. It also contains a magnet. The piston and the yoke are magnetically coupled. As the piston moves, the yoke moves exactly the same distance. Rodless cylinders are ideal for long-stroke applications, effective up to 10 meters. Multi-positioning can also be achieved using cylinders, in this case with valves and multiple sensors. Another form of multi-positioning uses two double-acting cylinders joined together. If the cylinders are of different length, this design is capable of achieving 4 different positions.
Class, while positioning is important, now you understand that it is also important for you to know the position of a particular piston. Okay, we had taken an example of a double acting cylinder in our process, that we have seen that there were two magnetic reed switches which were also determining the position. Okay, so for a particular process, the position of cylinder is also a matter of concern. Okay, so when you are going to define a particular process, it is very important that once if the cylinder has reached to its extended position, until and unless it is not retracted, your process should not start. Okay, okay, this is very much important. So the this is just a simple example. Okay, and it is important for you to understand that how and where we can use the positioning sensors. Okay, so we have used magnetic reed sensors for these. Okay, and what kind of other sensors can be compatible with the pneumatic cylinder? Can you tell me what kind of sensor can be compatible apart from the magnetic reed switch? Now yeah, can you answer that? What can be the other kind of, can photoelectric sensor work uh, for determining the position of cylinder? Can photoelectric sensor be utilized for determining the position of cylinder? Answer yes or no. Nayan, Kalpana, Adarsh, Bhanu, Ritik, Aprajita, Shubham, Hitesh, kindly respond to this. I'll repeat my question. Yeah, yeah, yeah. Hitendra, we can't use photoelectric sensor here because piston is inside the cylinder. Okay, so the piston position cannot be depicted by a photoelectric sensor. Therefore, we use magnetic reed switches for that. Okay, or we can use Hall effect sensor also. Okay, positioning is important. And for that, you should know that how in a process a pneumatic is working, how and when in a particular process a pneumatic cylinder will be extracted or retracted. And when you are going to learn about that whether it is extracted or retracted, you need to learn a little bit about pneumatics also. Okay, so therefore this session is very much important.
For example, the four positions are used in this machine to drill and countersink two holes.
See now, in this particular example, we had two drills. In this particular example,
This machine to drill and countersink two holes.
just have a very deep understanding of this particular process. I'm going to ask questions related to this process. I'm just repeating this.
For example, the four positions are used in this machine to drill and countersink two holes.
Again, I am repeating this process. Just have a very quick review of that, and I am going to ask the questions related to that drilling.
Achieving four different positions. For example, the four positions are used in this machine to drill and countersink two holes.
So for this cylinder, how many times for this particular process, how many times does the cylinder has moved? How many times the cylinder has changed its position? There are four holes. Okay, there are four holes, and how many times this has changed its position? Can you tell me that? Do you want to look at the process once again, class? Do you want to look at the process once again? Okay, okay. So just yeah. So just count it, okay, and give me that answer. Okay, I'm just repeating this.
Can also be achieved using cylinders, in this case with valves and multiple sensors. Another form of multi-positioning uses two double-acting cylinders joined together. If the cylinders are of different length, this design is capable of achieving four different positions. For example, the four positions are used in this machine to drill and countersink two holes.
Yeah, now can you answer? Bhanu is answering 8, Nayan is answering 9, Hitesh answered 9. Muskan answered 8. 9. Okay, 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 okay. Most okay. If I had asked this questions to uh, say 100 students, it always happens that 50 students say 9 and 50 students say 8. Okay, so there are four holes. Okay, so four for one stroke for drilling, one stroke for encompassing. Okay, okay, so there will be two process for each of them. Yes, so there will be 8 strokes for four holes, but while it was picking it up through vacuum, there was one extra process. So there were 9 strokes regarding that. Plus one for picking. Yes, Nayan, very good. I think all of you have answered, those who have answered 9, they have added that plus one for picking. Okay. Now you can understand that it has provided a stroke for 9 times for a very single and a very simple operation. Okay. Now you have to make a particular sequence chart regarding this particular process, but in order to understand that how the process is working, how the process is going, you must understand that what is happening in the pneumatics. Okay, how the pneumatics is changing, how you are going to control it. Okay, so there should be a particular position regarding a particular pneumatic position, there should be a sequence related to it. So in order to maintain a sequence, okay, you need to understand the position of pneumatics, and for that you should know that how pneumatics work and how pneumatics is controlled by electropneumatics, how that electronics is induced into that. Because a very simple thing is this, that a directional control valve is just changing the direction of air in pneumatics, but at what point of time in a particular process what kind of actuation is required in order to shift a single process, that for that pneumatics is important. A very brief understanding of pneumatics is important for that, and this is why this integration is important for every kind of engineer irrespective of domain. Okay, so we have completed this. Now let us just look at the pneumatic actuators of rotary kind.
Cylinders convert pneumatic energy into mechanical energy. So far, you've seen how this produces linear motion. Here, the linear motion is converted into rotary motion through a gear train. As the piston rod moves, the rack on the end of the piston rod turns a gear, producing rotary motion. As the piston moves left and right, the gear rotates in the opposite direction. This machine uses a rotary cylinder to convert pneumatic energy into a powerful force for a stamping operation. Another design is the rotating vane cylinder. In it, compressed air directly produces the rotation. It functions in the same way as a double-acting cylinder in that it has fixed stops at both ends of the stroke and performs work in both directions. In this type of cylinder, the angle of rotation is adjustable. Rotary cylinders can be used in a number of applications. In this example, it's moving parts from a test station to a conveyor belt. Another use is for parts orientation. Here, a rotary vane cylinder is used to turn parts over for machining on the opposite side. Rotary motion can also be accomplished through other designs. One design, the rotating vane motor, is capable of producing continuous rotation. This pneumatic screwdriver can reach speeds between 3,000 and 8,000 RPM. The vane motor works by means of a rotor located off-center in a cylindrical chamber. Movable vanes located in rotor slots are forced outward against the chamber walls, sealing the individual chambers. Air enters the smallest chamber, turning the rotor as it expands with the increase in chamber size. The air is then exhausted when the chamber reaches its maximum size. Rotating vane cylinders are available in right, left, or switchable rotating versions. At this workstation, 2 vane motors are used to drive pneumatic screwdrivers for the assembly of electric motors. One advantage of pneumatic motors is that they can be used for applications in which a maximum torque should not be exceeded. This is the symbol for a rotary actuator with a limited angle of rotation. A different symbol is used to represent rotary actuators with unlimited rotation called pneumatic motors. These are a good example of how symbols reflect component function rather than structure.
So till now we understood that what kind of actuation can occur. Okay, so how can we actuate a particular, you can say actuator, pneumatic actuator, and change the positions. Okay, but you have seen that you need to change the direction of compressed air and change the direction or the location of exhaust simultaneously in order to change the positions. Okay, so that switching has been done through valves. Okay, so now let us discuss that how that switching of air has been done. Okay, so how that complete circuit switches itself, so we get different positions for different actuators.
In pneumatics, valves serve a number of functions. They can be used to open and close flow paths, regulate pressure, adjust flow volume, and direct flow through various paths. One type of valve is the directional control valve. It has 3 basic functions. They are to block the flow path, to open the flow path, and to direct flow. Directional control valves perform all 3 of these functions when they're connected to a cylinder. Next, let's examine the types of directional control valves. This directional control valve can be used to control a single acting cylinder. It has 3 passageways called ports. The one at the top is connected to the cylinder. At the bottom left is an exhaust port, and the port on the right is connected to a source of compressed air. The valve also has 2 switching positions. With 3 ports and 2 positions, it is called a 3-2 directional control valve. This design of the valve seat and seals is called a poppet valve. 3-2 directional control valves are represented by the ISO symbol on the right. This valve is shown with a push-button actuation and spring return. Unactuated, the valve blocks the flow of air to the cylinder, and air exhausts from the piston side, allowing the spring to hold the cylinder retracted. When the button is pressed, the valve shifts, connecting the compressed air port to the cylinder. This causes the cylinder to extend, and the valve blocks the exhaust port. When the push button is released, the spring built into the valve shifts it back to its starting position. The cylinder is then connected to the exhaust port, and the cylinder spring returns the cylinder to its initial position. In this industrial application of a manually actuated 3-2 directional control valve, the single-acting cylinder ejects finished parts from a clamping device when the button is pushed. Next, let's examine the 5-2 directional control valve. Like the 3-2 valve, the 5-2 valve has 2 positions, actuated and unactuated. However, this valve has 5 ports. It's represented by this ISO symbol. The 5-2 valve is used to control double-acting cylinders. Both parts at the top of the valve are connected to the cylinder. The center port on the bottom of the valve is connected to air. The 2 outside ports are exhaust ports. In its initial position, the valve directs air to the piston rod side of the cylinder, holding it in place. When the push button is pressed, the valve directs air into the piston side of the cylinder. At the same time, it exhausts air from the piston rod side. When the push button is released, the valve directs air into the piston rod side of the cylinder. At the same time, it exhausts air from the piston side. Double-acting cylinders are used in applications where work is done in both directions. For example, this clamping fixture uses compressed air to hold the plate in position. This is another type of valve, the 5-3 directional control valve. It has three possible positions: center, right actuated, and left actuated. Notice that there are two springs in the valve. These return the valve to the center position when the push button is released. The valve is represented by this ISO symbol. The 5-3 valve can be used to control the position of a rotary vane double-acting cylinder. The valve port connections are the same as the 5-2 valve. Both upper ports are connected to the cylinder. The lower ports are exhaust, air, and exhaust. In the valve's initial position, all ports are blocked. This holds the vane at its current location. Pressing the left push button sends air into the left side of the cylinder and exhausts the right side.
So class, just have a focus on this particular type of arrangement. And let me just add on one thing to this. This kind of arrangement is used for hydraulic cranes also. Okay, so you can understand when you need to hold on a particular position or to shift a particular position, you need a 5/3 valve. And when you just need switching of two positions, then you need 5/2. Now the abbreviation is according to that only. If I am saying 5/2, that means that there are 5 ports and 2 directions or 2 positions of a particular valve. In this particular example, it is saying that it is a 5/3 valve. Well, so there are 5 ports. You can see there are 5 ports: 1, 2, 3, 4, 5, and there are 3 positions for this. Okay, so extreme left, extreme right, and center position. So when there are 3 positions, 5 ports, it is a 5/3 valve. And when there are 5 positions and 5 ports and 2 positions, then it is a 5/2 valve. Okay.
Rotating the vane. Pressing the right push button sends the air into the right side of the cylinder, rotating the vane in the opposite direction. When both push buttons are released, the springs in the valve return it to the center position, and the cylinder is held in position at various rotation angles. This is a typical application of a 5-3 directional control valve. The operator can stop and hold the parts bin at any angle. There are 2 ways valves can be controlled. Directional control valves can be directly actuated, as shown by this roller lever actuation, or indirectly controlled by another valve, such as this push-button 3-2 valve controlling a 5-2 valve.
The only difference in today's technology is that we are using, rather than from manual control, we are using an electric control, and rather using another valve, we are using what? In e-pneumatics, what we use for changing the direction in DCVs? We have already discussed it. Solenoid. Yes, Ritik, very correct. We use solenoid. Yes, we use solenoid. Yeah. So the technology is same. The only thing is that now we control it with solenoid, and now solenoid is working as an operator actuator. It is also actuating a particular DCV, and the solenoid get excited from by getting an output from a relay get excited through the signal that it gets from PLC. Okay, and a PLC gives a particular signal for the excitement by a certain logic, and that logic can be activated through a particular sequence, whether it is from actuation through a switch or sensor or anything else. Okay, so this is the line of control by which it gets controlled. Okay, so but still you need to understand that what pneumatic valves are.
The AND valve enables the logical AND decision to be made pneumatically. Therefore, the piston extends only when both push buttons are pressed simultaneously. AND valves are also called two-pressure valves. This shows how the two-pressure valve operates. When air enters the valve from one side, the output is blocked. If this signal is lost and air enters the valve from the opposite side, the output is also blocked. Only when two signals enter the valve is an output signal produced. At this workstation, two parts are pressed into a housing. Two conditions must be met in order for the pressing operation to start. They are: a start signal must be present, and the machine must have completed the previous cycle. This is indicated by a limit switch located at the initial position of the cylinder. Often, machine circuits use multiple AND valves. To simplify circuit plumbing, you can use a valve block containing multiple valves. For example, this block contains 3 AND valves. Another type of logic valve is the OR valve. When one or more signals is received by this valve, it produces an output. OR valves are also called shuttle valves. As shown by this diagram, the OR valve has 2 input ports and 1 output. When a signal is received at either input port, the valve passes the signal to the output port. If 2 signals are received by the valve, the first signal produces an output and the second signal is ignored. A shuttle valve is used on this machine so that it can be started from either of 2 locations. The machine can be started by pressing a push button, or a foot pedal can be used to start the operation. The machine starts if a signal is received from either location. The 2 signals are connected together in this OR valve. Next, let's examine another type of valve, the quick exhaust valve. One way to increase actuator speed is to exhaust cylinders directly to atmosphere through the large opening in a quick exhaust valve. This avoids the longer and narrower flow passages through the directional control valves. In this example, only the first cylinder has a quick exhaust valve. When started at the same time, the first cylinder extends faster. When installed on large cylinders, the quick exhaust valve has a more noticeable effect. Using quick exhaust valves in control circuits results in higher machine cycle times and greater productivity. In applications that use large cylinders, the advantages of the quick exhaust valve are obvious. One type of pressure valve is the pressure regulator. It's responsible for holding the operating pressure constant by regulating the flow orifice. When the pressure increases, the valve automatically closes partway, reducing the flow to the circuit. The pressure regulator also smooths out pressure spikes from the machine circuit by venting excess pressure through atmosphere. Every service unit contains a pressure regulator. Next, let's examine another type of regulating valve. This is an adjustable flow control valve. Air passes through a restriction in the valve. When the size of the restriction in the valve is reduced by tightening the thumb screw, less air passes through the valve. This is a one-way flow control valve. As its name implies, the valve controls flow in only one direction. It consists of an adjustable flow control and a check valve. The flow control restricts the flow of air in one direction. In the opposite direction, the check valve opens, allowing air to bypass the flow control. One application of the one-way flow control valve is to control actuator speed in one direction and allow full speed in the opposite direction. In this machine, the piston extends slowly and then retracts at its normal speed. One type of combination valve is a sequence valve. This valve switches when a predetermined pressure is reached. In this machine, the sequence valve controls the pressure applied in pressing a shaft into a housing. Pressure valve waits until the shaft reaches the bottom of the hole. When the circuit pressure rises, it sends a signal to retract the cylinder. Another type of combination valve is the time delay. It contains a one-way flow control valve, air reservoir, and directional control valve. This valve delays the sending of a signal for a set time. The length of the time delay is controlled by adjusting the rate at which air is allowed to enter the reservoir through a flow control. Once the reservoir is filled, the directional control valve shifts, allowing the signal to continue through the circuit. In this application, the time delay valve holds the cylinder in position for a few seconds to ensure that the screw is fully seated in the hole. Earlier in this video, you learned about two types of valve actuation, direct and indirect. This is an example of direct actuation. The control valve is directly actuated by the push button. Indirect control is actually the preferred type of actuation because it allows for separation of signal input and processing. One reason this is desirable in machine design is that it allows you to include logic functions in the circuit. To understand this better, let's examine a number of applications. In this machine, signal input is provided by the machine operator. As long as the operator presses both push buttons, the cylinder continues to extend. When the operator releases either button, the cylinder retracts. Therefore, the cylinder movement is manually controlled by the operator. This circuit contains an example of automatic signal input. When the piston reaches the end of its stroke, it actuates a limit switch. The signal generated by the limit switch shifts the 5-2 directional control valve, moving the piston back to its initial position. In most applications, the roller lever actuated valve is a sensor. It generates a signal based on the position of moving parts in the machine. Here, a limit switch is used to create an automatic return circuit. Once the operator presses the push button, The sequence continues automatically until the cylinder returns to its initial position. This is the result of the interaction between piston rod, sensors, and control valves. Now that you are familiar with the individual components used in pneumatic circuits, let's examine how they form pneumatic control systems. The first component is the service unit. It's the link between the air distribution system and the pneumatic control circuit. Remember, it controls the pressure supplied to the circuit, cleans the air, and can add oil to lubricate the circuit components. The next step is to select the components that will actually perform the work. For this example, let's use a double-acting cylinder. If you connect the service unit directly to the cylinder, it will extend. However, this does not allow you to retract the cylinder. You could move the air line to the opposite port on the cylinder, retracting the cylinder. Now, when you want to extend the cylinder, you have to move the air line again. This is not a safe or practical control method. Therefore, a directional control valve is used to connect the cylinder to the service unit. This is a simple control system that provides direct actuation. In most applications, it's rare for cylinders to be directly actuated. Normally, control and signaling are accomplished using discrete components. In this circuit, two push-button directional control valves send signals to a 5-2 directional control valve. When a push button is pressed, the cylinder is actuated. Another benefit of indirect control is that even if one of the push buttons is pressed momentarily, the cylinder will complete its full operation. This is because the control element stores the signal. Another consideration is to incorporate safety features into the control system. For example, a second push-button valve was added to the extend side of this circuit. This design requires that the operator use both hands, pressing both push buttons at the same time to extend the cylinder. An AND valve is included in the circuit to provide this function. In order for the cylinder to retract, the third push button must be pressed. The structure of the pneumatic control system can be described in terms of the functions of the circuit components. The first level is the source of energy and its preparation. The second level contains components that initiate control signals. Logic functions that process these signals are located in the third level. These determine conditions that must be met before actuators are moved. The fourth level contains control elements that send air to the actuators. The fifth level contains the actuators, but not all control circuits contain separate components for each level. In simple circuits, one component may provide the functions of multiple levels. This push-button actuated directional control valve provides the functions of signaling, logic, and direct control. Next, let's look at the 5 levels using ISO symbols to represent the components. At the first level, we have the energy supply and the double-acting cylinder in the level of actuators. A 5-2 valve is used to actuate the cylinder. In this constellation, the manually operated valve acts as an input element, processing element, and final control element. We then used, in our example, 2 push buttons as signal elements to actuate the directional control valve. The 5-2 valve acts as processing element and final control element in this case. To enable the AND function to the circuit, a 2-pressure valve is used as processing element. Let's look again at the 5 principal levels of a pneumatic circuit. Energy supply, signal elements, processing elements, control elements, actuators. Each of these levels can be identified in the actual machine circuit. The service unit is the source of energy and its preparation. The 2 manually operated valves initiate control signals. This AND valve provides a logic function. The 5-2 directional control valve is the control element, and the double-acting cylinder is the actuator. Regardless of their complexity, all pneumatic control systems contain these basic functional levels.
Abhay, your question is, do we need to learn all type of pneumatics? No, but you just have to look at the applications that are related to it. Okay, so one will be about the vacuum generation. Okay, one will be about the vacuum generation. Class, just give me a minute. I have a urgent call. Yes, Abhay, you don't have to learn all the types of pneumatics. You just need to enjoy the process only. Okay, just don't get panicked with it. You need to understand that how air goes, how air flows. But the thing is that what you need to understand is about the process, how it is integrated to a particular process. You need not to learn all type of pneumatics. Okay, that whether it is rotary, what will be the diameter, but you need to understand that how to read a particular pneumatic diagram, because you need to understand a particular system, and in order to understand a particular system you need to look at the system's energy flow, and when you are looking at energy flow you have to deal with pneumatics, and when you are dealing with pneumatics you have to see the manual that how a pneumatic energy is flowing through a particular path, and you have to make a logic also. Okay, as an manager or as an producer of a particular process, you need to understand that what will be the logic behind a particular process. There can be n number of processes, but until and unless you don't know that how you will integrate your actuation with your process, will you be that much comfortable with the process while making a particular process, Abhay? Okay, just a very brief knowledge that how pneumatic works. Okay. Now, and just to improve your overall vision towards a particular process, this lecture was a very brief introduction of pneumatics is important. You need not to learn anything. You need not to cram anything. Okay. You just need to understand it how it is related to factory automation. It was a older video. You might have seen these kind of machines, but these kind of machines are only there in our industries. Okay. The only difference is that the pneumatic switches are converted into electro-pneumatics. So your PLC has taken the place of the pneumatic control system. The pneumatic control system actuation is the similar kind of actuation. Okay, but the buttons that they were pushing manually, now they are being pushed um, automatically, and that automation is done through PLC. Okay, so that force that was required to push the button, or the button is not required, that logic is now saved in your programmable logic controller, and that logic works with the process, it integrates with the process. Once we will get into each and every station, that how a particular logic is working, how we can create a particular logic. So for that, a sequence is important, and in order to learn a particular sequence, you need to understand that how pneumatics is working. You need not to learn or cram anything. Okay, Abhay, is that fine? You need not to learn that. Okay, okay, okay. You need not to learn about each and everything into the pneumatics, just how the process is working. We have a particular system. This video was important just to let you know that how this process is automated. We will continue with this pneumatics in the rest of the session also. Okay, so everyone is aligned with this. Kindly respond yes or no, that what pneumatics is, how we can relate it to pneumatics. Because a very brief this is also working for us, that we have used a very old video, or this is the only video that has been shown in all the pneumatic classes everywhere in every practice, because this is one of the very basic from where pneumatic has started, and we have already covered that pneumatic control system was somewhat switched with automation. Okay, so this was the pure pneumatic control where manually we were controlling it. The only difference is you will always see a directional control valve in an industry. You will always see a pneumatic cylinder in an industry. Now, apart from the manual control, the only difference is that you will have a electro pneumatic system. You will have an electronically controlled directional control valve, where rather than from pushing a button, you will just actuate a solenoid through a particular logic, and that logic will be given through PLC. Okay, so can we take a break now, and we will continue at 4? Okay, okay. So we will meet at 4. Let us take a break.